Hello everyone, in this video I will talk about master production scheduling and I will shortly call this as MPS. In the previous weeks we started talking about ERP systems. In fact, ERP systems are software systems that integrate the application programs in different departments of a company. For example, these departments may be finance department, sales department, marketing department, manufacturing department, or human resources department, etc. And we call these application programs in these different departments as the modules of ERP systems. And in this course, we will cover some of the modules of the ERP systems. We will start with the manufacturing module. And master production scheduling is one of the important operations done in this module. And in fact, MPS is the disaggregated version of the sales and operations plan. In the previous semester, in fact, we discussed sales and operations plan. Remember that for periods we made the production plans of a company and made decisions whether to hold inventory or not, or whether to hire workers or fire workers, etc. And we made this plan for product families. And now MPS is the disaggregated version of this plan. It states which end items or product options manufacturing will build in the future. And MPS is a statement of planned future output. It specifies the products that will be completed, the time of completion, and the quantities to be completed. It is not a statement of demand, it is a statement of production. It specifies how product will be supplied to meet future demand. And also, MPS is not a forecast. It differs from the forecast in significant ways. In fact, forecast is an important input into the planning process that determines the master production schedule, MPS. MPS takes into account capacity limitations, the cost of production, and other resource considerations, and the sales and operation plan. Now I will talk about the business environment for the MPS. Three main production environments have been identified. These are make to stock, make to order, and assemble to order. And each of these environments affects the design of the MPS systems. Primarily, they affect the choice of the unit used for stating the MPS. This unit used can be end item terms, some average end item, product modules or options, or specific customer orders. According to the business environment, we will choose these units. And in fact, some of the companies may use more than one business environment. Let's start with make to stock. Make to stock companies carry finished goods inventories for most of its end items. And the choice of MPS unit for these companies is fairly straightforward. They use the end item catalog numbers. But some of them may tend to group these end items into model groupings until the latest possible time in the final assembly schedule. For example, there is a company called Allen Furniture Company. They use a consolidated item number for items identical except for the finish color. In fact, what they do is that they produce their furnitures to the stock, but they do not carry out the last operation, that is coloring. And when they get the orders from the customers and when they learn the color of the furniture that the customers require, then they make the last operation, that is coloring, and complete the products and send to the customers. And second business environment is the make to order. In this environment, we cannot predict the customer's exact need because there is a very large number of possible production configurations. For that reason, companies cannot make to stock. They have to wait until they get the orders from the companies before starting to produce their products. And in this business environment, customers expect to wait for a large portion of the entire design and manufacturing lead time. And in make-to-order company, the MPS unit is typically defined as the particular end item or set of items composing a customer order. And the third business environment is the assemble to order. Again, just like the previous business environment, I mean make to order, in this business environment there is a large number of possible production configurations. For that reason, it is difficult to predict the customer needs. But in this environment, customer delivery time requirements are often shorter than total manufacturing lead times. So production must be started in anticipation of customer orders. Before taking the customer orders, the company starts to produce the components and sub-assemblies of the final products, and when they get the orders, they make the assembly by using these components and sub-assemblies and produce the final product. For example, we can give some examples to these companies, I mean using assemble to order. For example, the computer company Dell. Dell has endless variety of computer and item combinations. And there is a company, sister company, producing forklift trucks with such options as engine type, lift height, cab design, speed, type of lift mechanism, and safety equipment. And lastly, for example, Mack Trucks, they produce trucks with many driver owner specified options. And none of these firms know until the last minute the specific choices their customer will make. For example, when I was an undergraduate student for my capstone project, I worked in Türk Traktör for a year. And while I was working there daily, they were producing approximately 100 tractors. And none of these tractors was same as the other tractor, because customers were specifying, for example, the color of the tractor, or they mention if they want air conditioner or not, etc. There were enormous number of options, and for that reason the company was producing the sub-assemblies of the tractors, and when they get the orders from the customers, according to these orders, they were making the final assemble of the tractors and were producing the final products. And now linkages to other company activities. Here in this figure, here you see the master production scheduling MPS, and as I mentioned before, in fact, demand management is an important input for MPS, and also sales and operations planning is an input for MPS. Also, rough cut capacity planning is an input for MPS, and also MPS is also affecting rough cut capacity planning. And then MPS is an input for the detailed material planning that we will call it as MRP, and in the next lectures we will start talking about MRP. Now let's discuss all these operations one by one. Let's start with demand management. It collects data on all sources of demand for manufacturing capacity, customer orders, forecast of future customer orders, warehouse replenishments, interplant transfers, spare parts requirements, and so forth. And these forecasts are summarized and provided to sales and operations planning. Moreover, demand management books customer orders. It enters the order, determines a delivery date with the customer, and provides product details to manufacturing. And lastly, these booked orders are also provided to master production scheduling to coordinate product availability with customer requirements. And secondly, sales and operations planning. In sales and operations planning, the forecasts from demand management will be consolidated and incorporated into the sales and operations plan. The operations plan is a statement of the aggregate output that will meet the objectives of the firm both quantitatively and qualitatively. In some firms, this plan is stated in terms of sales dollars generated for the company as a whole or for individual plants or regions. In other firms, it is stated as the number of units of output to be produced in the next year. The aggregate operations plan constrains the MPS because the sum of the detailed MPS quantities must always equal to the whole as defined by the operations plan. And lastly, there is rough cut capacity planning. And this involves an analysis of the master production schedule to discover the existence of any manufacturing resources that represent potential bottlenecks in the production flow. This is the linkage that provides a rough evaluation of potential capacity problems with a particular MPS. And if any problems are disclosed, they must be resolved before attempting to execute the MPS. Now we will start talking about master production scheduling techniques. Firstly, I start with the time phase record to show relationships between production output, the forecast, and expected inventory balance. Then I will show how plans are revised as you roll through time during a review cycle. And lastly, I represent the process for promising delivery to customers. Now I will show you the time phase record of a company for MPS. Here is an example. In this example we have 5 periods, and here in this row we see the forecast for each of the periods. And now we will make the master production schedule. Companies may have different strategies for their schedules, and in this example a level strategy is used. The production level is kept constant. When we calculate the total forecast, we see that it is 43, and when we produce 10 units of products in each period, we are able to meet the customer orders. So here, as you can see, we produce 10 units of products in each period. But instead of level strategy, the company may prefer to apply another strategy, for example, a chase strategy or some other type of mixed strategy. The exact strategy chosen depends on the characteristics of the process employed for making the item and the constraints within the company. The goal is to find the plan that best balances cost and benefits. And now let's continue with this example. An example with the level strategy. Now we will calculate the projected available balance. On hand, at the beginning of the first period, we have an inventory at an amount of 20. And what we do to calculate this projected available balance is that we take the on-hand inventory and we sum the MPS amount and then subtract our forecast. and we obtain 25 for the first period. And to be able to calculate the projected available balance for the second period, what we do is that we take the previous projected available balance, that's 25, sum the master production schedule, and subtract forecast and obtain 30. And here is the formula for the projected available balance. And when we have positive projected available balance for each of the periods, it means that we are able to meet the demand in each period. Now, in the previous example, we assumed that we do not have a lot size for the production, but we may have a lot size. What I mean with the lot size is that, same production process is used to make different items. And when production switch from one item to the next, this switching usually involves some change over time. And to minimize the impact of the loss of production due to the changeover, parts are made in batches rather than one at a time. And the number of units made in a batch is referred to as the lot size. And now, for this example, the lot size is determined as 30 units. Okay, it is given here. And moreover, we have a safety stock of 5 units. In fact, the safety stock is a precaution against uncertainty in demand. And also, when we have such an amount for the safety stock, when the projected available balance is less than the safety stock, we understand that we should schedule in production. Okay. Now let's make this plan again. Okay. In this case, we have a lot size and also safety stock. And we calculate the projected available balance for the first period, it is 15. Then for the second period, it is 10. And assume that we do not produce any products. Let's calculate the projected available balance for the third period. 10 plus we do not produce anything, so we cannot sum the MPS. Subtract the forecast, then it should be 2. It is under the safety stock, so we don't want to be under the safety stock, so we schedule a production on the third period. And the lot size is 30, so we produce products at an amount of 30 at the third period, and we continue to calculate the projected available balance. And as you can see, there is no need to produce in the other periods because in the projected available balance we are over the safety stock. And now I will talk about rolling through time. These manufacturing systems are dynamic systems. We have to make updates continuously. For example, assume that now we are at the second period. The first period passed, and in this example, the forecast for the first period was 5, but the actual demand was 10 instead of 5. Now here you see that on-hand inventory becomes 10 because previously we had 20 units on-hand inventory. Since the demand was 10 instead of 5, now we have an on-hand inventory at an amount of 10. And in here we scheduled a production at the third period, and we keep this. And when we keep this production plan, and when we calculate the projected available balance, we see that there are negative numbers in many of the periods. By the way, also here the expected demand has changed. In the previous table, you see that we have such forecast for the periods, but since we had a higher order at the first period, we update our forecast for the rest of the periods and we obtain such a forecast. And here we see that we are not able to meet the demand in these 4 periods. So we have to update this plan. What we have to do is that since we have a negative number here, quickly we schedule a production on the second period, and moreover, not to be under the safety stock, we have to schedule a production on the third period and also on the 5th period. Okay, this is our new plan. So what we have to do is that when a period passes, we have to update the forecast and we have to check our plans if they are okay or not. Now, after updating this plan, of course, we have to ask some questions. Now, the first question is that does the company have the capacity to immediately produce a batch that was originally scheduled for period 3? It is important. Moreover, can the company produce batches in 2 consecutive periods in the future? You see, we scheduled production in 2 consecutive periods, so we should check if it is possible or not. Moreover, is material available to meet the requirements of this schedule? Okay. And lastly, high costs are typically associated with making production changes. The master production schedule should be buffered from overreaction with changes made only when essential. Of course, we shouldn't make changes if it is not required, but for this example, we see that it is required to make these changes. Okay, we try to make these changes, but while making these changes, we have to answer also these questions. Okay, in the MPS, we should check the capacity constraints and also we should check the material requirements if it is possible to produce these products with this schedule or not. Now I will introduce a new concept called available to promise, and I will shortly call this as ATP. For many products, customers do not expect immediate delivery, but they place their orders for future delivery. And they may either ask when the order can be shipped or specifies a desired shipment date. And order promising can be coordinated with production schedules by using a concept known as ATP. Now, let's continue with the same example. Here, now we add a new row called orders. These numbers shows the deliveries that will be done in these periods. And now we will calculate the ATP. For example, for the first period, we have an inventory level of 20, and we know that there will be a production in the third period at an amount of 30, and we will increase our inventory level in this period. Until this period, we are checking the delivery amounts. In the first period, there is a delivery of 5 units, and in the second period, there is a delivery of 3 units, totally 8 units. And we have already on-hand inventory at an amount of 20. So we subtract this delivery amount from this on-hand inventory, and we can say that in the first period, the available to promise is 20. And for the third period, now we know that we have a production and we will increase our inventory level with this production amount, I mean 30. And let's check the delivery amounts after this period. In the third period we have 2, but we have no delivery in the fourth and fifth period. So in the third period we can say that 30 minus 2, the ATP value is 28. And also this is the discrete case. We can also use the cumulative version of ATP. Here in the discrete case, in the third period, ATP value is 28, but we already have an ATP value as 12 from the first period. In fact, the cumulative ATP value is 40 in the third period. Let me summarize how we calculate these ATP values. First, for the discrete case. For the first period, ATP is equal to on hand plus MPS value. In this example, we have no MPS value in the first period. For that reason, it was 0. And we subtract the sum of the orders until the next MPS. And we obtain this first ATP value. And for each period when a subsequent MPS occurs, ATP value is equal to MPS minus sum of the orders until the next MPS, as we calculated in the third period. And for the cumulative case, for the first period, it is same with the discrete case. I mean, ATP is equal to on hand plus MPS minus sum of the orders until the next MPS. But for the periods when a subsequent MPS occurs, ATP is equal to previous ATP plus MPS minus sum of the order until the next MPS. And this is the summary how we calculate the ATP values. And for the projected available inventory, here, when we calculate the projected available inventory, in the example, you may see that we use the forecast values, because forecast values are more than these delivery amounts. But if we had a higher value here, I mean in the deliveries, we should have used that value. I mean, we check the forecast and the order delivery amounts and choose the higher value and calculate the projected available balance according to this higher number. And the reason is that in fact this is a conservative approach and our hope is that during a period we will eventually sell up to the forecast, and if this proves to be true, we want to reflect the additional sales in projecting our inventory balance. And some experts refer to this as consuming the forecast. Now, by using these ATP values, let's check if we have a new order, if it is possible to supply this new order or not. We have such new orders, 4 new orders. Here is the amounts, and these are the desired weeks for these orders. In fact, these are the amounts that we will ship. I mean, we have additional amounts for our delivery amounts. So we add these new amounts to our orders, our delivery amounts. Here we add 5 for the second period, 15 for the third period, and we do not have any delivery in the fifth and sixth period, and with this new order we have deliveries in these periods also. And we update our calculations. We calculate our projected available balance and ATP value and obtain such a schedule. And we see that If we keep the previous schedule, I mean make a production in the third period and do not make any production in the other periods, as you can see in the schedule, the projected available balance is negative in the fifth and sixth periods. So it means that we are not able to supply these new orders with the current schedule. So we have to update our schedule. So we update our schedule and we also make production in the fifth and sixth periods. And these are the tables updated. The first one calculates the ATP value with the discrete version, and in the second table we see the ATP value with the cumulative version. And when we check this cumulative version, we see that we have no negative values at the ATP value. So in this case, we are able to supply all the demand, all the new orders. The use of both the projected available balance and the available to promise row is the key to effective master production scheduling. In fact, using ATP to book orders means that it is unlikely that a customer promise will be made that cannot be kept. This may mean some orders must be booked at the end of a planning horizon, concurrent with creating an additional MPS order. And as actual orders are booked, the available to promise row provides a signal for the creation of new MPS orders. I already talked about different business environments, and one of these is the assemble to order environment. In such an environment, the variety of the end products is really high. For that reason, the companies have difficulty to predict the demand of the customers. For that reason, mostly the companies produce the components and sub-assemblies of the final products, and when they get the order from the customer, by using these components and sub-assemblies, they produce the end items. Let me define bill of materials. In fact, we will discuss bill of materials in detail when we discuss MRP in the next weeks. But let me shortly define it. It specifies the ingredients required to make each part or assembly in the system. It is a listing of all sub-assemblies, intermediates, parts and raw materials that go into a parent assembly, showing the quantity of each required to make an assembly. The bill of materials may also be called the formula, recipe, or ingredients list in certain process industries. Now here, this is an assemble to order environment. We have components and we have options. We combine these components and options and obtain the end items. And for this environment, we will use two-level MPS. And now let me define super bill that we use in two-level MPS. In fact, super bill is again bill of materials, but it is a special type of bill of materials. The super bill describes the related options or modules that make up the average end item. For example, think about a computer with 2 GB of memory. In its super bill, we can have the components as, for example, 0.5 web cameras, 0.3 cell phone interface modems, and 0.8 extra high contrast displays. In fact, it is not possible to produce such an end item, with half web camera. But it means that, in fact, the super bill gives us such an information. It means that when customers require a computer with 2 GB of memory, 50% of the time they require web cameras, but 50% of the time they do not require. And 30% of the time they require cell phone interface modems, and 70% of the time they do not require. Like that. And this super bill is in fact provides a very useful information for planning and master scheduling. Let me give you an example for the super bill. Here we have an end item. This is rototiller. As you can see in the picture, it is this device. And this rototiller have these options. For the horsepower, it has 3 options as 3 horsepower, 4 horsepower and 5 horsepower. For the drivetrain, we have 2 options as chain and gear. And for the brand name, we have 3 options as Taylor, Garden Till and OEM. And in the end, when we multiply the number of these options, we see that we have 18 different end items. And here is a super bill for the 4 horsepower rototiller. Okay, here we have common parts, and we use these common parts for all the rototillers. But here we have the options for the drivetrain, gear and chain, and it says that 60% of the time it is gear and 40% of the time it is chain. And here also safety stock of these components are given. And here we have options for the brand name, and it says that 40% of the time it is Taylor, 50% of the time it is Garden Till, and 10% of the time it is OEM. This is a super bill. And by using this super bill, we carry out 2-level MPS. For example, the company is planning to produce 100 4 horsepower tillers in each period. Here you see the orders and the calculations are done as we discussed previously. I mean projected available balance, available to promise, and master production schedule. And we have no safety stock for this end item. And now again we will create MPS tables for the components. For example, for the Taylor brand and for the OEM brand, these are the MPS tables for these components. And let's check the super bill. Let's check the Taylor brand, for example. It is saying that 40% of the time it is Taylor brand, and for the OEM it is 10% of the time. So if we are planning to produce 100 end products, and if we know that 40% of the time it is Taylor brand, then we take the 40% of the amount of the end product, that is 40. And we produce 40 of this component in each period. And for the other component, it is in the super bill, it is given that it is 10%, and we take the 10% of the amount of the final product and produce 10 in each period for this component. And we calculate the projected available balance and available to promise for each of these components and check if our plan is okay or not. And this one is the discrete version for the available to promise values, and this one is the cumulative version for the available to promise values. And we see that we have no negative values, so we can say that our schedule is okay. And this is the 2-level MPS for the assemble to order business environments. Now I will talk about master production schedule stability. Too many changes in the MPS are costly in terms of reduced productivity. However, too few changes can lead to poor customer service levels and increased inventory. And our objective is to strike a balance where stability is monitored and managed. So, for that reason, we may define time fences. For example, let me give you an example, and it is a common practice in fact, 8, 16 and 24 weeks. What we mean with these time fences is that for the first time fence, I mean 8 weeks, we call this as a freeze period. I mean, when we make our plan, when we create our MPS, we say that this is a freeze period. It means that we cannot make any change in this period. For the next time fence, I mean between weeks 8 and 16, MPS is again quite rigid, but minor changes within the model series can be made if components parts are available. And for the weeks between 16 and 24, substitutions of one end item for another would be permitted, provided required parts would be available and the production plan was not violated. By creating these time fences and by creating these rules, in fact, we create a balance for the stability of MPS. And now I will conclude this video with these concluding principles for the MPS. The MPS unit should reflect the company's approach to the business environment in which it operates. The MPS function should use the common ERP database if such a system is implemented in the firm. Common systems, time phase processing, and MPS techniques facilitate effective scheduling regardless of the firm's environment. Customer order promising should be closely linked to the MPS. Available to promise information should be derived from the MPS and provided to the sales department. A final assembly schedule should be used to convert the anticipated build schedule into the final build schedule. The master production scheduler must keep the sum of the parts equal to the whole. And that is all that I would like to talk in this video. Thank you for listening to me. See you next week.